Yeah, welcome everybody, and it's my pleasure to start this new trimester of the SEED seminar about flavors of amplitude. And our first speaker is Julio Parra-Martinez from IHES, telling us about Feynman periods in classical and quantum field theory.
Okay, thanks a lot, and let me start thanking the organizers for inviting me, but also for organizing this whole series of SEED seminars over time. Whenever I could come, I enjoyed it. I think it's really nice for the community here in Paris. Actually, how many people here think of this as mathematicians? And how many persons? So maybe mathematicians can raise their hands. Okay. Okay, the rest I will assume they're physicists. Okay, so this talk is supposed to be directed to both. So the idea, because there's going to be this whole trimester on amplitudes, I thought rather than present some new technical thing, I'll just give a basic introduction to the story of Feynman integrals, Feynman periods, with a bit of a kind of historical perspective, and also with view to what are kind of state-of-the-art things that people are trying to do, or that are appearing in actual calculations in physics, and also what I think are some of the open problems that might be of interest also to mathematicians. So yeah, it's going to be very basic. So the people who already know all about perturbative computations in quantum field theory might be bored, but I think it's probably a good idea for the rest of this trimester. So okay, and one of the points I will try to make is that a lot of this story people thought that it was restricted to kind of the sort of numbers that we compute in quantum field theory, but it turns out that these things also appear in classical field theory, and I will give you what I think is the reason why people didn't notice until recently, that you just need fields. You don't need h bar anywhere in the business to find that there's this interesting functions and numbers appearing. Okay, so let me first start the old story, which is actually the quantum part, right? So how do these periods? I will later, for the ones that don't know, explain what I mean by periods. But how did the story start in quantum field theory? Okay, so in quantum field theory, the object that we're interested in is a scattering amplitude. And so some S matrix elements. So we have some particles with some momenta P1, P2, P3, P4. And then we ask, what is the probability amplitude that this initial state was left in the final state? And there's some complex number that tells us this. And then Feynman taught us that there is a way to compute this at this in expansion in some small parameter with the sum over diagrams that correspond to all possible histories of some process. And then to each diagram we can associate some integral. Okay? So each graph we can associate some integral. So just to set up the stage, so some random graph, right? So here we would have this external momenta, et cetera, et cetera. This would have two loops. So I would say that this has L equals 2, and then N equals 4, where N typically I refer to how many external legs this graph has. Okay, and then Feynman told us a set of rules to compute some complex number which is associated to this graph. Okay, so so typically this will be some integral over some rational differential form over some projective space. But there's multiple representations. So let me just mention some of the ones that are common. So the one that Feynman gave us directly is something that we call the momentum space. Basically like a circuit representation. So the prescription here is simple. So to each one of these legs, we associate some mass, some positive number, and then some vector. Okay, so different from these ones. And then we solve Kirchhoff's rules. So we just solve that all of the momenta that come in and out of any vertex, so these are directed, they have to add up to 0. Okay. And then maybe to each vertex also we can associate some other rule to generate a number. So these diagrams will be given by kind of some integral of whatever momenta are not fixed by solving this what we call momentum conservation, which is just Kirchhoff's rules for this graph. So there will be a bunch of momentum. In fact, as many as the number of loops. There's a numerator, and then there's a product of what we call propagators, which are things that look like P of L for each leg, which is internal, plus m squared with the tangent to bottom. Okay, so it's a simple prescription that tells you what to write, and then off you go. You have to go and compute this number and add them all, and that gives you the scattering. Okay. Let me give you two other representations that people like. So another one is what we'll call Feynman parameters, or Feynman parameters. Okay, so this one, instead of these vectors, what we associate to each leg is some homogeneous coordinate in projective space, and then this looks something like an integral. They have like a volume form of E with a number of edges, internal edges, and then there's two polynomials, which one can compute. So this is basically has to do with some sum over trees. All possible trees, there's a rule to associate different monomials to this polynomial, which are products of these homogeneous coordinates. And then this one is the same thing, sum over all possible two trees, or two forests, I think people call it. So ways to divide the graph in pairs of trees, and also there's some rule to associate to each one of those a monomial in this thing. Okay. And again, okay, the integration cycle here is over all of RD for each one of these variables that we call the momenta. Here is some simplex in this projective space. Okay. And then a recent presentation is the last one I will write about. So the Bikov representation, which has become very popular lately. So this, what we do is we associate each one of these propagators. We call it some complex variable z, which is precisely when you change variables to go from this to that. And then this now looks very simple. This is basically the form of visible zi. Maybe there's some extra ones which I don't divide by, and then there's some polynomial, which is called the Bikov polynomial, raised in power. And these are also raised in power, which depend on d and l and number of legs and so on. Okay. So there's a ton of representations. Everyone has their favorite, but of course they all compute the same numbers. And okay, so why it is interesting? Physically, they compute something that we care about, which are these probability amplitudes. Now, mathematically, they're interesting because okay, this is an integral of differential form. There's some singularity locus of the denominator. Okay. So this now is supposed to give some interesting transcendental numbers in general. So the simplest example is dz over z that gives us some logarithm. Okay, so more generally, what we get is that each diagram gives something that looks like this. So it's integral over some form. Then this form has some singularity locus, which is some variety x. Okay, so some curve. And then I hope here that and typically something that is defined maybe by some inequalities or something like that. And this is something which is typically rational. So this is actually a period as was defined by Kulsevich and Zagier, which the most basic definition is the integral of some form which is rational or algebraic over some domain that you can also define with like algebraic equation. Okay. Now more precisely, actually this is so this form lives in some like middle cohomology of some projective space modulo this x and relative to the boundary of this cycle. Sometimes you need to be careful because these things may intersect and the definition is a bit more complicated. But and then you're pairing this with the right class in homology, and this computes some number that you care about. So in general, this because this is singular, this is actually a period of what mathematicians call some mixed hot structure. Okay, so just a cohomology associated with some generate complex algebra. Okay, and by the way, why do we call this period? So typically, a cartoon picture of this is I have my integration cycle, and then I have somewhere where this x, where this is singular, right? Now, what's interesting in this will depend on some physical parameters. We call them SI. So these are the kinematics of my process. Okay, but mathematically, this is just whatever moduli your curve has that changes its shape. And then as you move this around, what happens that your singularities can move around, and in particular, you can pick up either some residue, you cross some branch cut of the resulting function, or something like that. Okay, and this is now a period more, I think the more usual definition, like the residue of some pole or something like that. So 2 pi times I, or more generally, more complicated. Okay, so what I want to do now is I want to give some timeline of the study of these things in physics, and then I will do it in math, and I will try to explain what have been, in my opinion, some of the kind of important, or maybe some less important than others, but some of the kind of checkpoints along the history of the study of these Feynman integrals. Okay, so we'll start in the 40s. So this is Feynman. So he just told us the rules to compute these things, in principle, to write some integral that then we still need to compute. Okay, and then actually it took about 20 years to people to start studying these things more carefully. And in 59, there was an important work by Landau, where he wrote, I won't delve in this, but he wrote just some set of equations that tell you what are the possible singularities that the function can have as a function of these external parameters. Okay, so these external parameters are the energies, the momenta of the particles involved in your scattering process, or just mathematically the moduli of your so-called. Okay, so he just wrote some set of equations which are hard to solve, actually pretty hard to solve, that in principle tell you the location of all possible branch points for this thing. Okay, then around the same time, there was famous paper by Karpowski, which tell us how to compute actually the discontinuity across some of those branch points. Okay, so this is something called the cutting rules, which is some set of rules. Again, if I give you an integral and you ask what is the discontinuity when I kind of give a phase to some particular variable of these external variables, then for some of them he gave a set of rules to compute these things. Okay. Still in the 60s, there's a book that appeared by Hua on tablets, which I think is the first time that there was some kind of more mathematical connection between Feynman integrals and things that other people might be interested in. So they recognize that the right thing to try to the right framework to try to understand this is precisely the framework of sort of homology theory that describes the cycle that you're integrating over and the properties and how it relates to various singularities of the integrand as they move around. So, for instance, they understood this criterion, these equations that Landau gave as the criterion for some singularities to pinch the contour, which is one of the ways that you can develop a singularity, and things like that. Okay, so this is the story of the homology of the integrals. Okay, but this is also around the time where, okay, so the 60s there were many developments about scattering amplitudes, but shortly after people discovered QCD, and they kind of they left this kind of more formal study of amplitudes for a while. Key development, more generally in field theory, actually has been very important for practical calculations from that point on. So So here, Tufte and Feynman introduced dimensional regularization, usually called dim-reg. Okay, so I didn't make, I wrote D on the board when I wrote these integrals over one. So in principle, these are integrals over some projective spaces of fixed dimension that they explain that by working with one of these other representations, one can immediately continue in this parameter D, and this is a useful thing to do. Okay, but mathematically, this back then it was a bit confusing, but okay, I'll comment in a second. But okay, this is what we call a regulator, so just a way to make all of these integrals, which in principle can be divergent finite. But it turns out that it's a very good regulator, and it has some magical properties that have enabled a lot of technology. Okay. Okay. So for instance, one of the pieces of technology. So now I'm going to change. I'm not going to mention the people anymore because I think they're not dead. So well, I guess but I just mentioned mostly the technique. Okay, but I'll mention the name. So this is what we. So there was a Cheturkin and Chakov. Chakachov, sorry. Introduced this idea of integration by parts identities, which is the statement that if one computes these integrals in this dimensional regularization scheme, then total derivatives with respect to these variables L, they're always zero by definition. Okay, so there's never boundary terms when we do integration by parts. This is a special property of this way of interpreting these integrals. Okay, and this can be used to find linear relations between all of your integrals. Okay, so in principle, when you try to do some computation, there's many integrals that show up. It's very hard to compute them. These things proliferate, and then they said, well, actually, it's a linear space. Okay, so you don't need to compute all of them separately. You can just solve these linear relations between them, and then try to go to a basis. Okay, and at the same time, well, I guess not at the same time, like 10 years later. There was the idea of solving these using differential equations. That was by Ponikov. That said, okay, well, if you can go to a basis, I can always differentiate the elements of the basis, and I could try to write them again in terms of the same basis. So there's, in general, if you have a basis of integrals, there's always going to be some linear differential equation. So this is derivative with respect to this S. This will depend on S, and also on this D, which is the dimension, which is some complex parameter in this dim-reg that will let me write some linear differential equation. Okay, so let's just solve these using differential equations. In a bit, I will write a dictionary between all of these things, concepts that might be more familiar for the mathematicians in the audience. Okay. Okay, so we're not done. We are just still 35 years ago. Okay, so what's the next thing? In 97, there's also an important development, which is called the method of regions by Menike and Smirnov. So what they said, well, actually, in many physical situations, we're not interested in the exact analytic dependence in all of these parameters, all these moduli. We're just interested in some limit. And they gave some prescription to compute asymptotic expansions of these integrals in those limits. Okay, I won't go into detail, but essentially it corresponds to giving some scaling in the limit to each one of the integration variables and just expanding the integrand. And it crucially relies on this, again, on this dimensional regularization way of interpreting these integrals, so as kind of analytic functions of the dimension. Right? And I'll say this at the end, but this is one of the things that I believe is still not understood mathematically. Okay, so there's this very powerful tool. We know how to use it. It gives the right answers, but it seems like black magic. We just have some tricks to compute these asymptotic expansions of these integrals, but there is no formal justification. And actually, it's more of an art than a science at this stage. So people don't understand for instance, how to prove that you found all possible regions, all possible scalings that the integral can have, or how to automate it, etc., etc. Okay.
But is it because you're doing some limit which is not, I don't know, some kind of under control, or is it because just
it's some prescription at the level of you have some representation of the integral, right? And then you say, okay, this depends on some parameters. Let me expand in some limit. And then they say, well, this in general will give you the wrong answer. But then if you assign to each integration variable also a scaling with respect to this limit, then you can find a correct expansion. And then, but then you say, okay, what scalings? Like, and then you have to try all possible things, and then see that there's a finite number of them that gives an answer which is not zero. And then if you add those and then you subtract the overlap, then you get the right answer. Okay, but I wouldn't say this is math at this stage. Like many of the other things that actually they're like very well understood mathematics. Okay, so I think also an important thing in 21, here I'll write a name because I think it's called the Laporta algorithm. But Laporta actually wrote an algorithm that shows how to always go to a finite basis here. So some kind of deterministic way of just solving these relations to actually achieve a basis. But this is still very hard. So there is an in-principle way you can call up this algorithm. If you wait long enough, you will find the basis. But in most actual applications, this is one of the main bottlenecks. Okay. So a lot of the developments of trying to understand the mathematics of Feynman integrals have to do with computing the integrals themselves and understanding this geometry behind it and all of that, right? These differential equations, as I mentioned in a second. But actually, in practice, the part that is hard is to solve this large set of linear relations. So one of the questions I mentioned at the end is, it would be nice if we can get some guidance from the geometry. It's telling us what is a good way of solving the system. We just write some system of equations, right? In the mathematical language, this is just corresponding to writing like explicitly exact forms. Okay, and then we use those to kind of modify them. So we go to some basis, some completely random basis for the cohomology of this thing. Okay, and then that completely random basis might be a good one, might be a bad one. Generally, it's a bad one. Okay, so then we have to work to find these differential equations, but maybe we could also get some guidance. Tell us, well, you should try to go to this kind of basis, and then you will find a simpler set of equations.
You mean good and bad depending on whether you're able or not to do the integral? Or...
Do the integral, and also in practice, you can see that if you choose one basis or another, the reduction itself could be
much smaller,
much faster, or much smaller. Also, like this is an infinite set of relations, even though there's a finite. But there's another whole business of how to choose good relations. Within that set. Okay, and then I'm almost done on the physics side. So, 2010, there was the introduction of kind of the symbol or coproduct on the functions that we get from Feynman integrals. So it was like Goncharov, Spratting, Bolovich, Vergu, and the people that told us, okay, well, sometimes you do a very hard calculation, but you can find some simplifications using some insight from math. And then I think since then, I just mentioned a couple of things. So there was a famous paper by Johannes Henn, which told us that at least experimentally, we can always find a basis where this differential equation is very nice. So this differential equation looks like there's always a basis of these master integrals, where it looks like d minus 4. So usually we live in 4 dimensions, so this is just our small parameter when we are regulating these things, times the matrix times the integrals, and this matrix doesn't depend on any dimension. Okay. So, and since typically we solve things as an expansion around 4 dimensions, this provides a very nice way to solve the differential equations. Okay. But how to find this basis, again, it's typically very complicated. So now people are understanding a lot of the geometry behind this. Okay, and then the last two things. 2018, we'll realize that actually one way to understand these integrals with these regulators is not thinking about regular homology theories, but this theory of twisted homology. Which precisely keeps track of this dependence and moves forward in some nice way. Okay, but one way to think of one of the insights for me, at least, from this business, was that when people try to understand the homology of these cycles and this whole business back in the day, this was very complicated because these things live in very high dimensions. It's very hard to imagine, compute the intersections, things like that. But one of the things they said is that there's actually also duals in cohomology of these things. So instead of looking at now things that have poles at this variety x and relative to this boundary, you can look at this. You can look at the opposite, where these have now zeros in x and perhaps poles at the boundary of the cycle. And these two things also pair nicely. Okay, so you can also just multiply a form here and a form here. And because this is a pole here, but this has a zero at this location, then this gives you some integral over the full space, so some projective space that lets you compute intersection products and decompose things in some basis. Okay, so I think this hasn't been exploited again very efficiently in the physics literature. I mean, people focus mostly on the twist, which is just saying that your integration by parts, your derivative is not usual derivative, is some covariant derivative. But I think this intersection pairing is something that should be useful, and I think people are not using to its full power. Okay, so this is very quickly, or maybe not so quickly, a lot of the history of Feynman integrals in physics. Let me just mention on the math side, I won't draw a whole timeline because I'll run out of time. But actually, around the same time as these guys, there was some work by Pham here in Paris, where he realized that a lot of this thing about the kind of homology of Feynman integrals and how to compute various discontinuities, which we call unitarity cuts, that the right setting was this Picard-Lefschetz theory. Okay, and there will be some of the talk that I mention this later. And this is a topic that has come back many years later when people try to understand actually cuts of Feynman integrals. Again, they learn that this is the right thing. But as it happens in this business, a lot of the progress happens because of people doing calculations. So I think there was a lot of work in the 90s by David Brockhurst and Dirk Primer, where they actually just computed a bunch of these things. Then they noticed that there were some interesting numbers, multiple zeta values that appeared that were interesting to mathematicians. And then, yeah, in around 2000, then Kunzevich and Taguier, they wrote this definition of periods. And okay, the rest is more or less history. But I think kind of the modern version of this, there's been a lot of work by Bloch, Brown, Pierre, Snow, and many other people, understanding that, okay, these are always periods for some kind of mixed model or something like that. And in particular, there's some action of some Galois group, which is what's behind this symbol of this co-product that should let us organize the space of these functions, and that physicists have used to simplify the results of our calculations. Okay, this is very quickly, but just to say that maybe the history is less long, but I think there's been a very nice interaction between physics and math, especially over the last 30 years, about this particular topic, and in particular here in Paris. So that's why I'm very glad that we're having this trimester about the topic. So, okay, before I explain something about kind of current status and also this classical limit that I promised, let me just write the dictionary so that people can talk to each other. Okay, so So when we talk about Feynman integral, this is typically some relative period. Okay. Right, so we have some cohomology relative to something having to do with the integration cycle, which is given to us by physics, and then we have to compute this. When we talk about cut integrals, this is kind of a usual period. You can think of it as some sort of residue of some rational differential forms, something like that. Okay, or IDPs, as I already mentioned, these are exact forms. Or master integrals are just a basis of this cohomology that we're interested in. Our parameters, our physical parameters, kinematics, typically the moduli of whatever variety we're interested in. And the last thing is that this differential equation that we write is precisely this Gauss-Manin connection, Manin, that describes the variation of the hot structure, mixed hot structure, which is associated with this variety. So all of these things people kind of discovered essentially independently, but it's of course the same thing. Okay, so what is the status of our ability to compute these things? And I'll talk about the status in physics, because this is what kind of matters to us for applications. But of course, there's been a lot of progress in some specific theories, computing things up to gazillion loops by many of our mathematician friends. So basically, if I just make a plot, which is number of these legs. Okay, so this is more accurate predictions in perturbation theory. This axis is more complex processes, so more particles involved in the processes. Then one loop and essentially solved in the late 90s and early 2000s by many people, but for instance, David here in the audience. Okay, so let's start here. 0, so just vacuum diagram. So even when you just draw graphs which don't have any external legs, okay. So this we can go all the way up 1, 2, 3, 4, until 5 loops, and this is more or less where the state of the art is. Okay. And then this is 0 or 1. These are essentially for 2. Then people can go essentially up until 4 loops. Maybe some examples at 5 loops. Okay, let's say all of these are done. 3, 5. Okay. So this is also done. This is basically done. This is the state of the art. So there's many examples. These are complicated things, and I would say that everything that lies here is complicated. So these are a few examples that I'll mention, but this is where the state of the art is. Okay, so we have a little corner of the whole space of perturbative predictions that people have understood over the years. So for instance, this is what you need to compute if you want to understand things like the QCD beta function, which is one of the 5 loops. This is what we need to compute if you want to understand like G-2. So these are kind of propagator integrals that have 2 external legs. This is what you need to compute if you want to understand, for instance, infrared divergences, so the pseudo form factor. And these are actual scattering amplitudes of things that we observe in colliders. Okay, and here there's also some example for black hole scattering. So we put a star, because this is very, very recent, where there's been a lot of exciting progress. Okay, so I would say that my estimate of the complexity of these things is that it's some function. I don't know if it's exponential or what, but I would say that it grows roughly equally with the number of loops and legs. There's another thing, which is number of scales, which I didn't write here. So of course, more particles means more scales. So this actually also grows faster. So there's some other number here greater than 1, at least 2. That's not that adding more scales, even if you put L and N, things become much more complicated. Okay, so so what do we get? What classes of functions do we get here? So if you look at this one loop, then these are always kind of generalized polylogs. So these are essentially iterated integrals for some Riemann sphere with like a bunch of punctures, okay, at different locations. So the moduli space is the location of these punctures, and then they can be at different places. So this is what people have found. And as I said, space is completely understood. We can essentially compute any one loop integral that we like. Okay, starting at 2 loops, we also get things like this, but we can also get periods of elliptic curves, or elliptic curves with mark points and things like that. So I think the most famous example is if you have this sort of integral that we call the sunset integral with different masses for each leg, or all of them are massive. This one 1.3. For instance, Bloch and Pierre did a lot of work on this. So these are periods of some particular elliptic curve. Which, by the way, this appears like the cut of these integrals. If I put all these propagators on shell, which I mean, means I put all of this denominator to 0, so I'm computing the residue. This is just some decay of some particle into 3 massive particles. For instance, if you compute muon decay in the standard model, okay, the mass reduction is tiny, but in principle, it's there. Okay, this should appear. It's mostly been studied in 2 dimensions, but we know how to relate to the 4-dimensional integral, and this will appear in some actual physical quantities. Okay, so another famous example is these integrals. So these are all massless now. But there's 10 external legs. So there was a paper by Simon Arnbot and Kasper Larsen where they argued that indeed the geometry associated with this integral is also some elliptic curve. Okay, so these appear, for instance, in scattering amplitudes in n equals 4 sigma. Okay, and okay, so we get like these generalized polylogs. We get things. We have genus 1 at 2 loops, and now we have many examples. So for instance, if you go these guys, you just add more legs. You can get periods of some K3 surface or general Calabi-Yau varieties, also the singular. If you add this thing here, also more loops. These are called train tracks. These are also related to some Calabi-Yau. Okay. There's other funny integrals that people call clarity which are I can show you the picture later. Okay, so we've seen that there's a lot more complicated things. So okay, so this class of periods, so these have to do with these mixed state motifs. So these are things that they're essentially like residues. So you just get factors of 2 by I when you compute non-trivial. But in all of these cases, one really needs to understand the whole mixed structure of the story, and I think we don't exploit all of the mathematical machinery nowadays in trying to calculate this. Okay, so this is all quantum. So what's the story classically? Why did we have to go to quantum theory to learn about this connection? So what is typically the thing that happens when you take the classical limit? Anyway, are there any questions before I move on? I'm trying not to be very technical and just give you a very kind of bird's eye view of things. But maybe sometimes that can also be too far from the ground. So let me pause for a second and see if you have a question. Okay, so what happens classically? So classically, you could also ask, okay, let me compute some amplitude for some process, and you know, essentially by the semi-classical approximation, by some saddle point approximation. So the leading term in the path integral will look something like some classical action divided by h bar. Okay, so this is just some function of sources you can imagine. Okay, and which class of diagrams do we get when we try to compute this? This is literally diagrams which are trees now, not loops. Okay, so they also have a bunch of legs, but they're contracted with the sources. Okay? These are j's that depend on something in space-time. Okay. However, we still need to integrate over the position of these sources, so you still get interesting integrals. Okay. Now, which integrals do you get? I think for intuition, it's okay, let me just say that generically this thing kind of looks like this. So these are the momenta of the sources. And again, there's some numerator and some denominator associated with each graph. Okay. And you see, because we still have all of these propagators. Okay, so we still have all of these legs in a graph that have things in the denominator. This should also give us some period. Okay. So as long as this thing can go to 0, so as long as one of these legs can go on shell, so one of these legs can satisfy p squared equals minus m squared, this is the Einstein relation. So as long as you can produce a particle, then you can have a singularity in this integral, and hence you should have some like interesting transcendental form. Okay, so just very quickly, like these periods have nothing to do with quantum; they just have to do with relativity, with particle production. Okay, so you don't expect them if you do some computation of some process, maybe in quantum mechanics, where you're not generating any particles, but in field theory, sorry, yeah, in quantum mechanics without particle production, but in field theory in general, where you can have radiation or just creating particles in some collision process, you should expect that you get similar things. Okay. In practice, why do we not notice? So I'll give you a very trivial example of what happens when you take some particular quantum integral and you take the classical limit. So let me look at this integral, where these are two massless legs and this is a massive leg. So it says m equals 0, m equals 0, and this has this momentum L, and this has a mass m. Okay, so this integral, it only has one loop, so it looks very simple. dvL 1 over L squared. Let me write this as P plus Q. So this is Q. And this is in the rules that I told you before. Okay, I have P plus L squared, which is the momentum going through here, minus m squared, which is the same as P dot L as possible, because P squared equals m squared, because this particle is real particle. Okay, so the classical limit, I won't go into detail, but you can think of, you have the content wavelength of the particle, which is h over m, and then this is much smaller than h over q. So q is the transfer momentum, which is roughly like a separation between the particles. And so this is the content wavelength, this is the separation. So classical, this means we're very, like, our distances are much longer than the content wavelength. So q is very small compared to m. So I can just expand it here. And by the way, I forgot, so there's an I epsilon prescription here, which has to do with the proper choice of contour. This will be important. Okay, so when I expand it, I can cross this term. And actually, you can easily convince yourself that the only part that contributes from this is the residue and this linear pole. Okay, so this thing actually looks like L squared, U squared, 2 pi I delta beta. So for instance, you can find it by averaging over like the two possible ways of labeling this, or like many ways of showing. Okay? So basically, this pi is the reason why we didn't notice. Okay. So generically, what we get is that when we compute one of these integrals in field theory, we get, so in general, L loops means some transcendental function of weight to L, okay, where a logarithm has weight 1, dialog has weight 2, and weight n polylog is basically n iterated integrals, and then pi has weight 1. Okay, so what happens classically is that actually every single loop gets a propagator that goes on shell. So there's always something that looks like this. And hence, actually, every single loop has an explicit factor of pi. So we're always looking at some discontinuity, effectively, when we're looking at the classical problem. So in fact, this gets halved, because this actually is, for classical, it looks like pi to the L times something that actually has weight L. So you need to go to very high orders to start noticing interesting things, okay? So typically, you need to go like at one loop, you can get up to dialogues. At classical, you can get up to a logarithm. Two loops, in principle, you could get something very complicated that at most you will get a dialogue. Okay? And people haven't computed to this order in classical field theory.
So, sorry, so you're saying you're just gonna end up always with one integration and that's it after the limit, or not?
So basically, you always took one residue in some variable. Okay, so you always get a factor of pi for free.
Okay.
Okay. So it's an integration over a smaller dimensional space, because you're basically intersecting with some hyperplane, if you wish.
Okay.
But the important thing is that a lot of the weight of these integrals gets absorbed by these factors in pi. So I think it's this very prosaic reason why people, even though they have been doing field theory for a long time, people hadn't computed to high order that you need to start noticing some of these things. Okay. Let me make one comment about this. How do we see that this has anything to do with the sources that I was saying? Okay, so let me give you an example. So if my source is actually a particle, which is what we deal with oftentimes in classical field theory, because when we ask what is the radiation by an electron, which is moving along some trajectory, right? The source will be something like an integral over some affine parameter along its world line of it would be a current, for instance, for electromagnetism. So this would be the velocity of this thing, or this is some parameterization of the curve, and then this would be an integral dv of x minus. So let's say it's traveling along a straight line, but this would be just u, and this would be u tau. Okay, so this is the trajectory, and this is x dot, so the time element of the trajectory. Okay. And then you can see that actually you Fourier transform this, then you get precisely u mu delta u dot use the Fourier. Okay, so this delta function is precisely this delta function here. That tells us that we have some particle that usually travel in a straight line. Okay, and we're always perturbing typically around straight trajectories when we do coefficient physics. So yeah, so these are the same thing. So this is just dealing with some classical source. And to find the factor of pi, you need to work pretty hard at that. Okay, any questions about this? Okay, so now I want to make another list of the things that we have found so far in some of these classical calculations. And then I'll just make some comments. Because actually this classical problem, despite the fact that things enter later, that also means we typically can go further. And there's been some spectacular progress. So these are practical people have found. And so the typical thing, so we have some observable, and we have computed essentially as an expansion in powers of G. This is Newton's constant, the mass of some particle, and Q is something like this momentum transfer that I was mentioning. Okay, so these are powers. So this is the sort of perturbation theory. We need to compute these numbers here. Okay, so this is called post-Minkowskian. So GPBN is called the n post-Minkowskian order. Okay, so you have this sort of axis where this is the number of loops, or kind of n. Where we call this m, not n. Okay. A plus 1 PM. Okay. So for instance, at 1 loop or 2 PM, what we found is that actually, even though there was supposed to be at least a log, we just found pi times some rational function. Okay. When we went to 2 loops, we just found logarithms. And when we went to 3 loops, we just found dialogues. Okay. Here we found generalized logs. Okay. But always of 1 weight lower than we expected. Okay. So I think this is one of the puzzles right now, which is that I told you before that we would expect that at some order in perturbation theory, at order L, we should get kind of pi to the L times some function that has weight L. Okay, but what we find in practice is that this is L minus 1 always. Okay. This is something that we don't understand, so I think we're still missing part of the picture. This is as far as polylogs are concerned. What about more complicated things?
But this is with practical examples, right?
Yeah, this is you actually do a calculation.
Yeah.
Then you, in intermediate steps, you have all of these things, but in the physical quantity, so this is not one of the individual periods. Individual periods always satisfy this rule, but when you plug them in to compute the final sum over all of the graphs, then we find that there's always a drop in all these values. So, so I think this is a puzzle. I think that there's some simplicity in the final answer that we don't understand. Okay, starting at this order, we find new things. Okay, so at 4 p.m., what we found is that there's actually a some periods of some elliptic curve. Okay, so some elliptic curve. So there's some Picard-Fuchs operator, which looks something like okay. The solution are just complete elliptic integrals, and it shows up in the answer for instance, the scattering angle of 2-point masses in perturbative GR. Okay, so this is actually some second order equation associated with this elliptic curve. In fact, what we find is that what appears are the periods squared, not actually the periods.
You mean
The square of the period, the square of the solutions. Okay, so this has 2 solutions on the elliptic integral the first kind and the second kind. And actually what we find is k squared, e squared, and kw in the answer.
Okay, the operator is a square and like
sorry, yes. This is it's second order. Okay, so in fact this is a hint of what lies ahead, because when people went to the next order, so when people went to this 5 p.m. order, what they found is something else. So what they found is periods of some particular free surface, of some family of K3 surfaces, parameterized by one variable, which is essentially the relative velocity, which is essentially this unit here. And actually the Picard-Fuchs operator associated to that is actually the symmetric square of the one for the elliptic curve. Okay, so the fact that here you have the square of the periods, it was a hint of what was coming at high orders. Okay, and this has to do with certain integrals that yes.
the Julio looks at, but at 4 p.m., this is precisely a K3 that we get. At 5 p.m., it's a bit the triangular frequency.
I will mention there's also the Calamity threefold.
This is a square, because this is a graphic, it meant this is why-
No, but we never needed to solve a fourth order Picard-Fuchs equation. We could always.
Problem.
Well,
It's a problem.
no, we could do it in terms of second order. We just saw the elliptic integrals.
Yeah.
Maybe you did the computation differently, but at least when we did it,
Yeah, the fact that it's product of the way you describe it, precisely because this is the different kind of.
I understand. Yeah, I understand. But if you didn't know about K3, you could have done the calculation. In fact, we didn't know about the K3, and we were able to do the calculation. But yes, I agree with you that in principle, the square of this solves that equation, not this equation. Yeah. Okay. Then, well, apart from this, there was also kind of series of subatomic polylogs. So these are iterating integrals of rational functions that have poles at the roots of unity. Okay, so and so these things are integrals that look like this. So they always look like some ladder integral. And in fact, these even appear in quantum in classical electrodynamics. If you go to like alpha to the 4, okay, to the 5th, sorry, in classical electrodynamics, then we also find that these things appear. Okay, so these generalized polylogs were there at high enough orders, even in classical electrodynamics. If you ask about the scattering of 2-point charges, these things appear. Okay. Yeah. So in fact, this thing was associated to some integral that look like this. Okay. And then here you found a more complicated integral, which is basically this, which had to do with this period of the state. Okay. And apart from that, there was a more complicated thing, which was a period some threefold, which does it to an integral x. Like this, and this, I can write it, so this looks like y squared x minus 1, z minus x minus u, z minus 1. Okay. So this is some actual hypergeometric example that people had studied in the past in the string literature. In fact, again, the Picard-Fuchs equation associated to this guy is actually this Hadamard product again of the. It's not this product; it's a different product of the second order for the elliptic curve. Okay, so these are the better known examples. Let me tell you about a couple more examples, and then I'll finish about others which haven't appeared yet in the literature, but that I think are interesting, as they appear in slightly different quantities. So in some work to appear with some collaborators, we've computed now a different quantity, so everyone has been very excited about the scattering angle, but of course, there's many observables in classical GR. So an interesting one is the power spectrum of the radiation for the scattering of a pair of point masses. Okay. Well, this is even at leading order is no one has computed. Well, now we have. So this is even at order G cubed. Okay. So this essentially looks like a kind of the integral over like a phase space of something like a 5-point amplitude squared with a fixed frequency. So for this moment in space, so k dot some vector, J2 time with some fixed frequency. Okay. So this depends now on two variables. It depends on kind of the velocity, which is this thing that was called u, and also depends on the frequency. And then what we find is okay, so we have two moduli in the problem. And then we find that the solution has to do with a family. So at each point of this space, there's a family of curves, of elliptic curves, which are actually not equal or isogynous, so they're just different, with a bunch of monotones. Okay, so the differential equation has this block structure. So this is basically the mixed block structure, where you have some block here, which is state. So these are just polylogs, and then you have some elliptic stuff here with punctures, so differentials of the third kind, and other elliptic stuff here, and then here it all mixes. Or these are mixed. They all mix with the same. Okay, so this is another interesting example where we found that you can also get these curves of elliptic curves, and okay, these are multi-scale now. Okay, so this is very different and in an interesting physical quantity. And then the other problem, okay, I could, if someone is interested, I can show you the J invariance later of these two curves to show you that they're really different. Okay, and the other thing is the actual main quantity that people are interested in, which is the waveform. So the actual gravitational field at infinity for the scattering of a pair of massive particles. Okay, so this is a two-loop order. Okay, so this is F mu, which is essentially the kind of 1/r part of the gravitational field at infinity. So this is what we measure when we measure the gravitational radiation. And this is hard because this is a 4-scale problem. Okay, so this depends on this velocity, it depends on the frequency or time, and it depends on two angles. It depends where you observe the celestial sphere, the radiation from the scattering process. Okay, and this is a two-loop problem, so it's at the very least elliptic with 4 scales, many master integrals. The cohomology is pretty large, so I think no one has computed this yet. It should be doable because it's just elliptic, but I think it's an interesting open problem. What one can do is one can look at something simpler. So what we were looking at with Davide here is you can look at the extreme mass ratio limit. So you can take the mass over do perturbation in the ratio of the masses. So we went to the first order in this perturbation, and then you can expand in small velocities. Okay, so you can expand basically when this u is much smaller than the speed of light. So this is what's called the post-Newtonian expansion, right? And there one can go to very high orders. So and by one I mean that guy. So I've been able to push this up until a couple of weeks ago, probably higher, but we can go to 9 p.m. order. And then we find that up until that order, everything one gets are these cyclotomic integrals. Okay, so probably to all orders in this problem, one finds this set of simple period as long as we expand the velocity. Okay? And this is also for a given multiple. So essentially, we reduce this to a bunch of numbers by doing the multiple expansion and then taking the small velocity. Okay, so and by the way, for the particle physicists, this 9 p.m. these are essentially like 8-loop HQT integrals. Okay, so this is not like a trivial thing. So this is a non-trivial calculation, and we think probably we can understand the structure to all orders in this velocity. Okay, so I'll just finish because I'm out of time. I just wanted to mention a couple of interesting questions that I think we have that, in particular, that could benefit from the interaction between physicists and mathematicians that care about these calculations. I already mentioned a couple of this. Okay. So the first one is, can the geometry guide this IVP problem? Okay. I told you that we just write all the linear relations between these things. We forget that there's any geometry associated to this thing, and we just solve them by some algorithm that someone wrote 35 years ago. Okay. And we don't give it much thought, but this is the true bottleneck of most calculations are this. So for instance, there was a paper a couple of days ago by the group in Humboldt, where they computed this 5 p.m. thing to the second order of this mass ratio expansion, and that requires something like 3 million core hours to get the reduction of IBP. And they noticed that they could only do it if they chose some very special basis, which they don't know why it's special, just so that things run much faster. Okay. So the answer to this is partial. So people have used the geometry to guide the differential equations. But it's always when you start with some nice integral that we understand, that we can study the geometry very, very carefully. We don't have like a tool that tells us how to choose a good basis again ahead of time. So these questions are related. So we know that there is a nice basis for the cohomology. Right? We know, for instance, that if we take the derivative of the differential of the third kind, it mixes with the rest, but the ones of the first and second kind, they don't mix with the third kind. Right? So there should be some basis that manifests this kind of lower triangular structure to begin with, but actually in practice, we need to work very hard to find that basis because we're just solving randomly these linear equivalents. And in that basis, the differential equation should also look much, much nicer, right? So I think we also need help in trying to use more effectively the understanding of the geometry and this cohomology of this variable. Okay. Then, as I said, I think it would be nice to have like a mathematical understanding of these method regions. This is really the workhorse for a lot of real-world calculations again, and a lot of our understanding of effective field theory. So I don't know what the right mathematical setting is there. There is a lot of work on this theory of limiting hot structures, right? Of what happens when you go to some singular point, some singular variety coming from something smoother, and how the hot structure degenerates and things like that. But okay, does this relate to this protrusion that we have? Is there a way to prove that this method of regions is consistent? I think. Then, just last two things. I think it would be nice to also have some of these. I just mentioned it in passing, but there's this whole theory of these Galois actions, or coproduct, or simple polylogs. Now people start to understand how to extend this to more complicated cases. So there's two questions. One is beyond polylogs, for all of these more complicated periods. This should exist because people believe that there's this Galois action on periods, but also to the Fourier integrals. Because for many of these gravitational wave problems, we actually care of what the waveform looks like in the time domain. What we measure in the experiment is a separation between the masses that looks like this, right? And that is not a period. That is at best an exponential period. And I think if we understand a lot of the things that we understand in this setting here, I think there's many physical quantities that we will be able to calculate more efficiently. And then just very speculatively, we know that in the moduli space of generic varieties, there's very special points, right? There's points that have kind of special kind of arithmetic properties, that have additional symmetries, and this is something that is not used at all nowadays in trying to understand or compute time integrals. So I always wonder also if there is any application of these more arithmetic aspects of kind of algebraic geometric aspects of the study of this geometry. And I think with that I will end. Thanks everyone, and sorry for
Maybe we can take a couple of questions before the break. Maybe I can start with this one. So is there a way you can guess which geometry is beyond one of the integrals? Like if you just have the integral, how do you know?
Yeah, so basically you need to look at this singularity locus of these various polynomials that appear. So that is the curve, essentially. Now, typically it's very high dimension. So that's why we go to a representation where it looks like kind of a bunch of hyperplanes intersecting something, and then we go where we do the locus of intersection of these hyperplanes. So this is what we call the maximal cut of the integral, and then you have a function of few variables that you can try to understand. But because in general we have L times D variables at least, maybe a few less. But when you are at 4 loops in 4 dimensions, that's 16 variables. Okay, so you can get it down by removing as many variables as propagators, so as edges in the graph you have, but then you still have some high-dimensional variety that you have to look at and understand.
And then that geometry is not related to the Calabi-Yau or...
That's the Calabi-Yau.
That's the Calabi-Yau.
That's literally the Calabi-Yau.
We know that there are things beyond Calabi-Yau.
Right.
Already have 2 loops. I mean, I don't know if any convention.
Yeah, of course, yes. I don't think they have appeared in any physical quantity yet.
No.
Yeah, but even the Calabi-Yaus have been recently done. So,
Maybe apart from GR, what are the application of this classical limit?
Well, I don't think there's many people that do classical electromagnetism.
Okay,
Because the classical limit there's another limit involved that I didn't mention. I just mentioned the H-bar counting. But if you want to do perturbation theory in classical electromagnetism, it's perturbation theory in the classical electron radius over R. And the classical electron radius is typically not large. So sorry, not small with respect to this. You need, for instance, atoms with very large Z. You can think as very classical. Okay, so if you have very large quantum numbers, okay, then that would be some classical limit. So maybe in quantum field theory, I think people look at, for instance, what happens when you have very large representations of the H group and UCD, and so there's also some semi-classics, things like that. I think there's some classical limit that might be related to some of these things. But yeah, for any practical applications, the only classical field theory where we need precision is in GR.
Any other question?
Or comments, because there's many experts in the audience. This was my very particular perspective on this business. But
maybe a comment that the transcendentality drop rate is just again doesn't happen in generic.
Right.
For the wavefront data.
Right.
Yeah, but the argument was good. It's just that sometimes it's too costly. And like
there's some simplification sometimes that we don't understand. Yeah, for instance, this K3 period also dropped out at leading order in the mass ratio, but now in the second order it appears. So there's all of these complicated things that we need to understand in intermediate steps, but oftentimes the final answer doesn't have for the angle.
Okay, let's thank Julio again.